By the end of the video, this diagram right here is going to make perfect sense to you, because today we're covering the Zeeman effect. The term Zeeman effect essentially refers to the splitting of spectral lines under the influence of a magnetic field, which means that this spectral line, for example, the D1 line in the sodium spectrum, which usually, with no magnetic field, looks like this, turns into this under the influence of a magnetic field. So this line splits into multiple close yet distinguishable lines. And this sodium doublet is also what we're going to focus on in this video. And just as a side note, the fact that this line is called D2 has nothing to do with deuterium or anything of that sort. When these lines were discovered, they were labeled alphabetically, and since sodium's D line is a doublet, we have D1 and D2. That's it. Now, in order to be able to understand the Zeeman effect, there are some prerequisites that are useful to know beforehand. I will do my best to explain each of these as we go, but you should, for example, know what a spectral line is, that when an electron goes from a higher state to a lower state, it loses energy, but that energy isn't just destroyed or disappears, but instead that transition from a higher to a lower state emits a photon. That photon has a certain wavelength, and that wavelength is what we see as a line on the spectrum of, for example, sodium. In addition, it's useful if you have at least heard of term symbols, so something like that, the quantum numbers of nuclear physics, and electric dipole selection rules for transitions. The Zeeman effect occurs when an external magnetic field exists, but is weak enough to leave the spin-orbit coupling intact. Spin-orbit coupling means that the angular momentum L and the spin are coupled into the total angular momentum J. When that is the case, the energy levels depend on the quantum numbers J and Mj, with Mj being the magnetic quantum number of this total angular momentum. This magnetic quantum number of J tells us basically how much of J points into the direction of the external field. But for the sake of this video, it's enough to simply know that Mj exists and that the energy levels of the Zeeman splitting depend on J and Mj. If the magnetic field becomes too strong and breaks apart the spin-orbit coupling so that L and S are no longer coupled into J, the paschen-Buck effect occurs, which we will cover in a different video. So for the Zeeman effect, we need a magnetic field, but it has to be weak enough to leave this coupling intact. As our example for this video, I have chosen the sodium D2 line. That line is emitted by this transition right here, from double P 3/2 to double S 1/2. These term symbols have to be interpreted in such a way that the blue number at the bottom is J, the large letter represents L, so the angular momentum, and L follows this letter coding right here. If you see S, that means angular momentum quantum number is 0. If you see D, that means angular momentum quantum number is 2, and so on. The small superscript number up here is 2s plus 1. So 2 times the spin plus 1. So if we look at double P 3/2, for example, we know that P stands for angular momentum quantum number equals 1. So we know that L is 1. We also know that J, the total angular momentum, is 3/2. And since 2 equals 2s plus 1, we also know that S is 1/2, because 2 times 1/2 is 1, plus 1 equals 2. So for this state, we have L equals 1, J equals 3/2, and S equals 1/2. But how can we find the allowed transitions? Well, transitions follow the electric dipole selection rules, which are these right here. The first two are essentially already represented by this transition right here. An allowed transition needs to have a difference in angular momentum of plus or minus 1, which is the case right here because P stands for L equals 1 and S stands for L equals 0. So we have a difference of minus 1, so we can tick that box. The second requirement for an allowed transition is that the difference in J, so the difference in the total angular momentum quantum number, is either 0 or plus or minus 1. Here we have J equals 3/2, here we have J equals 1/2, which is a difference of minus 1, so we can tick that box as well. Now, when an external magnetic field is present, this third selection rule becomes relevant. Recall that Mj is the magnetic quantum number of J. Mj can take on values from minus J going up in steps of 1 up to plus j. So in order to find the possible values of mj for this state right here, j is 3/2, so the first possible value of mj is minus 3/2. Now we increase in steps of 1, which gives us minus 1/2, plus 1 gives us 1/2, plus 1 gives us 3/2, which is plus j, and thus the maximum value for mj. Since we have 4 different values of mj, this state splits into 4 substates under the influence of a weak magnetic field. The end state of our transition has j equals 1/2, so the possible values of mj are minus 1/2 and 1/2. Under the influence of an external magnetic field, this state splits into 2 substates. Now, if you draw this stuff, it ends up looking like this. Our starting state has 4 different values of mj, so it splits into 4 different substates. Our end state has 2 different values of mj, so it splits into 2 different substates. But how do we actually know which transitions are allowed? Well, that's where this rule comes into play. For an allowed transition, the difference in mj has to be either 0 or plus or minus 1. So with that in mind, let's find all the allowed transitions, starting with the highest state, with mj equals 3/2. A change in mj of 0 isn't possible because we don't have mj equals 3/2 down here. A change of plus 1 isn't possible either, because in that case we would need 5/2 down here, which is not the case. So the only allowed transition from this highest state right here is the transition from 3/2 to 1/2, which represents a change in mj of minus 1. Looking at the second highest state, a change of 0 in mj is now possible, from 1/2 to 1/2, and a change of minus 1 is possible, from 1/2 to minus 1/2. A transition with a change in mj of plus 1 wouldn't make sense here, because 1/2 plus 1 would be 3/2, which doesn't exist down here. From minus 1/2 to 1/2, we have a change of plus 1, which is allowed. And from minus 1/2 to minus 1/2, we have a change of 0, which is allowed as well. Also, don't worry about the color coding. I'm going to explain that as soon as we have found all allowed transitions. For the lowest possible level of our starting state, which is minus 3/2, the only allowed transition is from minus 3/2 to minus 1/2, this one right here. And anything else would be either dipole forbidden or wouldn't make any sense in the first place. So these are all the allowed transitions from the split substates of this state to the split substates of this state. But why do we actually do this? Well, as I mentioned earlier, when we go from a higher state to a lower state, we have a loss of energy, and a photon is emitted with a certain wavelength. And the energy of that photon and its wavelength depend on the energy difference. So the higher the energy difference from the starting state to the end state, the more energy the emitted photon is going to have. And here, without a magnetic field, we have this energy difference, and this leads to a certain wavelength. But as you can see, for example, from this substate to this substate, the difference is much shorter. So this transition is going to emit a photon of a different wavelength. And that's how we can find the splitting of those spectral lines. I also color-coded these transitions because depending on the change in mj, we can learn about the polarization of the emitted light. If we have delta mj equals plus 1, we have right circular polarized light. If mj does not change, we have linear polarization. And if mj changes by minus 1, we have left circular polarization. In the next video about the Zeeman effect, we're going to calculate the Zeeman energy shift, which refers to the difference between the normal energy level and, for example, this energy level. So between the energy level without a magnetic field and between the split ones with the magnetic field. Once we know the energy shift, we can calculate the energy level of each of those substates, and once we know the energy levels, we can determine the energy difference and thus the wavelength of the emitted photon. So that's what we're going to cover in the next video. Thank you so much for watching. I wish you best of luck for whatever you need this for, and a wonderful day.